Welcome back, everyone. This is Discrete Math, Lecture 11, Sequences and Summations. Okay, so we're going to cover, of course, sequences, something called recurrence relations, and summations. All right, so last time we talked about sets, which were groups of objects that did not have to be in any particular order. Sequences are groups where the order is now going to matter. Okay, so these are ordered lists of elements. For example, we might have the list of numbers 1, 2, 3, 5, 8, or 1, 3, 9, 27, 81. And there's not just some order, but there's usually some sort of logic or some sort of formula to get from one element or two elements to the next element, right? For example, in this case, we're just adding, right? 3 is going to be the summation of 2 and 1. 5 is going to be the summation or the sum of 2 and 3. 8 is going to be the sum of 3 and 5, so on and so forth. Okay. From here, we're just we're multiplying from one element to another by 3. Okay. So these are sort of formulas, or there's some sort of logic behind what's going on here. And we're going to talk about different types of sequences and how we can determine what that next term is going to be in a sequence. But to start off, we're going to use our curly brackets and just a singular term a sub n to describe a sequence, and this is denoting all of those elements. Okay. We can also use what's called index notation. If we're starting from 0, then our first term is going to be a sub 0. If we're starting from 1, our first term is going to be a sub 1, right? And then we're just going to count up from there in either case. And this is going to be valuable because whatever formula you're using is often going to be determined in or described in terms of n being that index, right? So if n is going to start with 0, then probably we're not going to want n in a denominator or something like that, right? So that kind of factors in that sense. Okay. Let's look at an example first. So consider the sequence a sub n, where a sub n is equal to 1 over n. Okay. So this is that exact sort of example that I was just thinking of, right? So we're not going to start in this case with n equals 0. If a sub n is defined as 1 over n, let's start with a sub n, or a sub 1 in this case, right? So we've got a sub 1, a sub 2, a sub 3, so on and so forth. If we go and we actually use this formula now to expand this, the first term is going to be 1 over 1. The second term is 1 over 2, 1 over 3, 1 over 4, and so on. All right, and you can simplify these if you like. I'm just keeping them in this format so we can see how every term is related to that index that we've got. N equals 1, n equals 2, n equals 3, and so on. Okay. So that was a really simple example of a basic sequence. Now, like I said before, we've got different types of sequences and different types of formulas that will help us determine the next term in that sequence. So the first type is what's called an arithmetic sequence. So an arithmetic sequence is of this sort of form. You've got some value c that you're starting off with, and to that value, all we're doing is we're adding something. We're adding some term d, which is called the common difference. And from term to term, you just keep adding it. You just tack on another value of d. So instead of writing it in an expanded form, we can just write this as c plus 2d, c plus 3d, c plus 4d. Right, your nth term, you have n of these d's, right? So you don't need to list them out like that. You can just write them in a summarized sort of fashion, okay? And c and d are going to be real numbers. So let's look at an example. Let c equal 1, let d equal -1. In that case, your sequence is going to be starting off with 1, which was your c. And to that 1, we're adding -1. So 1 plus -1 is just going to be 0. Okay? To that, add another -1. We'll have -1. Add another -1. We'll have -2, and so on and so forth. Okay, so this is just going to become the numbers from 1 and lower. Okay, integers from 1 and lower. In another case, we could have c equals 7, d is equal to -3. We start with our 7, and we're going to subtract 3 from that, or add -3 from that, however you want to think of it. Okay, so we go from 7 to 4, 4 to 1, 1 to -2, -2 to -5, and so on. Okay, let's see if we can identify C and D for the following sequence. So we've got 100, we've got 50, we've got 0, -50. So we're just dropping by 50 every term, right? And we're starting at 100, so our initial term C is 100. D, the thing that we're adding to go from one term to the next, is just -50, okay? And that formula, remember, in an arithmetic sequence is presuming that you're adding something. So even if you're going down, then you can still just be adding a negative number, okay? That's our first type of sequence. Our second type of sequence, that follows in easy, sort of predictable mathematical pattern, is what's called a geometric sequence, okay? A geometric sequence now is of this sort of form. Instead of adding or subtracting something, now we're multiplying by something. So we've still got our initial term C, and now we're going to be multiplying by what's called the common ratio R, okay? And again, these are real numbers. Okay, so for our first term, we've got C times R to the 0, which is the same thing as C, but I'm just writing this here to show you how many factors of R there are over here, okay? Then we've got a single factor of R, 2 factors of R, and as we go into this, the nth term is going to have n factors of R, okay? So what does this look like? Let's suppose C is equal to 1, R is equal to -1. Well, if we're just multiplying by -1 to go from one term to the next, then we're just going to be oscillating between +1 and -1. Okay. In another case, we might have C is equal to 2 and R is equal to 5. So we start with 2, and to go from that to the next term, we just multiply by 5, we get 10. Multiply by 5 again, you get 50, and so on. Okay. So let's see, if we're going to identify C and R for the following sequence, well, C is what we're starting with, which is 1,000. And then we're going from 1,000 to -500, back to +250, back to -125, right? So I should have a negative sign in my common ratio. And every single time, the absolute value of these terms is halving, right? So my R should be -1/2. C is equal to 1,000, R is equal to -1/2. Okay, well, that brings us to our next topic of interest, which is what's called recurrence relations. Okay, so a recurrence relation for our sequence A sub n is going to be an equation that expresses A sub n in terms of one or more of the previous terms of the sequence. Okay, so it could be A sub 0, A sub 1, A sub n minus 1, right? Whatever, just the last term, the previous term before A sub n was. Okay, this is going to be for all integers n, where n is greater than or equal to n0, and n0 is a non-negative integer. This is just saying, right, n0 is just going to be our starting value, which we said was either 0 or 1. Okay, our index values are just counting numbers, right? So 0, 1, 2, so on and so forth. We're not going to ever have a negative value for an index. Okay. So let's see. A sequence is called a solution of a recurrence relation if its terms satisfy that recurrence relation. All right. And the initial conditions for a sequence specify the terms that precede the first term where the recurrence relation takes effect. So a recurrence relation is often not going to start from A0. Well, it can't start from A0, right? Because what's the preceding term? What can we define A0 in terms of that comes before it? Nothing. So oftentimes at least A sub 0 has to be given as an initial condition, okay? And oftentimes you'll have more, right? You can have A sub 1 also given as an initial condition. So however many previous terms your recurrence relation is making use of, if it's the previous two terms, well, then we had better been given the first two terms as initial conditions. If it's the previous three terms, then we're going to need the first three terms as initial conditions, right? So your recurrence relation is not going to just start off. We're not going to evaluate that for A0 or A1 usually, right? We're gonna start after that, whatever our initial conditions are. We could start off from A1 if all we need is one previous term, but it doesn't have to be that way. Okay, so let's see an example. Let A sub n be the sequence that satisfies the recurrence relation. A sub n is equal to A sub n minus 1 plus 3. Okay, so we're only making use of the last term, the term right before our nth term, and we're adding 3 to it. Okay, so this is going to be holding or taking effect from n equals 1 onwards. So the only initial condition that we need is A sub 0. If I have A sub 0, I can figure out what A sub 1 is. And then once I've got A sub 1, I can figure out A sub 2, and so on. I can figure out the rest of the terms. So then what are A sub 1, A sub 2, and A sub 3? Okay, well, this is our logic. This is our formula now for determining the nth term. We're given our initial condition, A sub 0. So for A sub 1, now I'm just showing here that really we can just plug in 1 for n in this formula. And you can do a little bit of arithmetic even in your index, but this is just a formalized way, a generalized way of referring to the last term. So for A sub 1, really what we're considering is A sub 0 and adding 3 to it. Okay, so we put in 2 for A sub 0, we add 3 to it, and our A sub 1 is 5. Okay, we can do the exact same thing for A sub 2. Well, we need to consider the A sub 2 minus 1 term, which is really just A sub 1. We plug in the 5 that we had just determined for A sub 1, add 3 to it, and we get that A sub 2 is 8. Same procedure. Take that 8 for A sub 2, add 3 to it again, and you'll get that A sub 3 is 11. Okay, so we can expand our sequence out with these new terms that we've discovered, 2, 5, 8, 11, and so on. All right, let's consider another example. This time, our recurrence relation is making use of the previous two terms. Okay, so it makes sense that we're going to have to start at n equals 2, and they're going to have to give us A sub 0 and A sub 1, because to start from here, we're going to need both of those. And it's going to be the difference of the last two terms. Okay, so A sub 0 is now given as 3, A sub 1 is given as 5. Find A2 and A3. Okay, so just to reiterate, this is saying take the previous term and subtract from that the term that came before it. So for A0 we have 3, A1 we have 5, A2 is going to be the difference of, well, A1 and A0, 5 minus 3. That difference will be 2. A3 is similarly going to be the difference between A2 and A1. Okay, go ahead, plug in that value for A2 that we just figured out. 2 minus 5, that's going to give us negative 3. So our sequence is going to look something like this: 3, 5, 2, -3, and so on. Okay. Then we've got what's called the Fibonacci sequence. So this is actually a pretty famous, pretty well-known sequence, and this follows a pattern. This is an example of something that we can describe using a recurrence relation. Okay. So we'll refer to the terms with this f for Fibonacci, f0, f1, f2, and so on. We start with our initial conditions. F0 is equal to 0, f1 is equal to 1, and the formula, the recurrence relation behind the Fibonacci sequence, is that f sub n is equal to the previous term, f sub n minus 1, plus 2 terms ago, f sub n minus 2, and this is going to be true for n equals 2 and onwards. All right, so what does that look like? Let's see if we can figure out what the next 5 terms are then. For f2, we just add up f1 and f0, which are just 1 and 0. We get 1 again. f3, take that 1, add it to the 1 from before that, and we get 2. Okay, so this is our f2 and f1. So the 1s did repeat here, but that's fine. That can happen in a sequence. There's no requirement that the terms necessarily be different, as long as they're following some sort of pattern, right? f4, take your f3, add it to f2, we're going to get 2 plus 1, we get 3. f5, f4 plus f3, which is going to be 3 plus 2, you're going to get 5. And finally f6, which is going to be f5 and f4, you're going to add your 5 and your 3, you're going to get 8. And if we were to list these out, we'll get 0, 1, 1, 2, 3, 5, 8, and so on. Okay. And the Fibonacci sequence is a special sequence in math. It's related to something called the golden ratio, and it has all sorts of applications graphically and so on. Okay. So that was just a quick look at how that sequence works. Next, we've got something called closed formulas. Okay. So we can represent recurrence relations and other sequences with explicit formulas known as closed formulas, okay? So recurrence relations are useful for telling me what a sub n is, but only if I know, right, some previous term, a sub n minus 1 or a sub n minus 2 or something like that, right? What if I want to know what a sub 4000 is and I haven't expend this? I don't know what the previous term a sub 3999 is, right? How can I do this? Well, I can use closed formulas, okay? So let's look at this example again. All right, so we had that same recurrence relation where I'm just taking the previous term and adding 3 to it for n equals 2, 3, 4, so on. I'm given that a sub 1 is equal to 2. Okay, well, I can use something called now forward substitution to determine this closed formula. And this is not really any different than our process or procedure that we've been using so far. But one thing we're going to do is we're not going to simplify right away, okay? So we've got a sub 1 is equal to 2. That's what we're given. Well, I'm going to add 3 to that as according to my recurrence relation. I'm going to leave that as 2 plus 3. I'm not going to simplify that to 5. Okay, so in other words, this is 2 plus 3 times 1. We do it again. Take your a2, add 3. This is the same thing as 2 plus 3, or 2 plus 3 times 2. So when those terms start kind of racking up, we can simplify them all into a single multiplication instead of several additions. Okay? a4, add 3 to a plus 3. Sorry, a sub 3. And you'll have 2 plus 3 times 3. Okay, so we see a pattern emerging. the number of 3's here that I have always seems to be one less than my index, okay? So I can now generalize this in this following format. A sub n, which is equal to a sub n minus 1 plus 3, is the same thing as 2 plus 3 times n minus 1. Okay, so this right here is my closed formula, and this is what would allow me to figure out a sub 4,000 or a sub, 82 million or something like that, right? This no longer depends on the previous term. I now just need to know my index. So whatever index I'm interested in, I can plug that in directly into here and figure out my formula. Okay, so this closed formula just resembles the same formula for an arithmetic sequence because that's exactly what this is. Okay, so that resembles something very similar to what we had here, right? And geometric sequences have their own closed formula as well. But the cool part is that closed formulas aren't exclusive to arithmetic sequences or geometric sequences. Even for more complicated recurrence relations, you can find closed formulas, okay? So for the same example, let's consider another method. It's called backward substitution. And in some cases, you might find this simpler. In other cases, it might be more difficult, but this is another approach to how we can figure out what that closed formula is. So now we start with that nth term recurrence relation, okay? And a sub n is defined as a sub n minus 1 plus 3. Well, what's a sub n minus 1? That is itself the previous term, a sub n minus 2 plus 3, okay? And you can kind of see what's going on here. We're going to, again, rack up 3's in a different way, right? We can expand a sub n minus 2 as a sub n minus 3 plus 3. Okay, keep an eye on those 3's, they're adding up. Okay, so if we do this, if we go back, well, I started with a sub n minus 1, right? I can keep going down this list, k times some other, right, iterative variable, k. It could be 50, it could be 100, it's just some general form, right? But I want to go back k times, and what's going to happen is my formula is going to become a sub n minus k plus 3 times k. So however many times I went back, that's however many times I'm going to have a 3. It's the same amount of 3's I'm going to have, okay? But this is only going to work if we can get all the way back, right? We don't still want this in terms of previous terms. We need to get back to some base initial conditions. So I need to make sure that instead of a sub n minus k, I have a sub 1 or a sub 0, right? So let's suppose we're going to go back to a sub 1 in this case. Then that n minus k needs to be equal to 1, right? The index here needs to be equal to the index here. They have to be the same thing. You can do a little bit of arithmetic. That just means that, well, k is n minus 1. I have to go back n minus 1 times to get back to my base case, okay, my initial case. Well, if that's true, then instead of k here, I can write n minus 1 and n minus 1, and that will show me this closed formula. As predicted, this is going to simplify to just 1, so a sub 1. I'm going to have plus 3 times n minus 1. Okay? And a sub 1, again, if we remember, was given as 2. Okay, that was our given initial condition. So we happen upon the same formula. A sub n is equal to 2, our initial condition, plus 3 times n minus 1. Okay? So in this case, yeah, I think backward substitution looked a little bit more complicated, but certain sequences or certain recurrence relations that you might come across, this might be the easier approach. Okay. So those are 2 methods for determining that closed formula, which does not depend on any previous terms, just your index. All right, and that brings us to our last topic for today's lecture, which is summations. Okay, so summations are sort of like sequences in that they're an ordered list of elements, but now instead of being separated by commas, our elements are going to be, well, added together. Okay, and so we've got a sum of terms, a sub m, so that's our first term, going all the way to a sub n. Okay, and it's from some sort of sequence potentially, but now we're adding them instead of just listing them out. Okay, we can denote this by this sort of notation. So we've got the Greek letter sigma here, and this means sum in mathematics. J is my index. It's going to be starting at m, and we're going to be going all the way up to n. Okay, so this is like your minimum, your starting value for your index. N is going to be your maximum value for your index. Okay, that's going to tell us how many terms we're adding, which terms we're adding. Okay, J doesn't have to be, say, 0. It could be, I could start with J equals 5, and I just want to add terms 5 through 10 together, something like that. Okay, so this is iterating through all of the integers, starting with the lower limit and ending with the upper limit. And that means exactly what we're saying. So we're going to have a sub m plus a sub m plus 1, all the way up to a sub n. All right. That index can also be referring to some sort of set. Okay, so it doesn't have to be a list of integers. It could be something like, well, I just want these values. Okay, so let's say I don't want to add up all of the numbers from the second to the 10th value in my list. I want to add up 2, 5, 7, and 10, just these specific ones. So I can define the set, and that iterative variable can just refer to those indexes in the set. Okay, so A2, A5, A7, A10. Yeah, let's look at an example here. We've got the sum from j equals 0 up to n of r raised to the j power, right? So this is just a simple power formula here, right? So you've got r to the 0 plus r to the 1 plus r to the 2, so on and so forth, all the way up to r to the n. And you can define n as some value, right? And in calculus, you do deal with summations as well in some higher level maths, and that n might actually go to infinity. Okay, so it doesn't necessarily even need to be a finite value when you're dealing with summations. And our purposes in discrete mathematics, we're typically not dealing with infinity. We're dealing with some finite defined value of n. Okay. Another example might be the summation from I equals 1 to n of 1 over I. Okay. And this will be expanded as 1 over 1 plus 1 over 2 plus 1 over 3, and so on, all the way out to 1 over n. Okay. And this series is actually known as the harmonic series. Okay, so this is an important series in mathematics as well. It comes up again in calculus and so on. Now here we're going to talk about some useful summation formulas that you might see over and over again. And it's going to be a sum and its closed form. So just like we can represent sequences with some sort of closed formula, we can do the same thing for summations, right? We don't have to actually sit there and add up all these terms. There's going to be some sort of nice pattern often that comes out of this. Okay, so if we had the summation from k equals 1 to sum n of your term k, so you're literally just adding 1 plus 2 plus 3, right? Some integers, some amount of integers. That's going to come out to n. times n plus 1 divided by 2. Okay, so to see an example of that, if your n was 100, if you're going to add up all of the numbers, all of the integers from 1 to 100, well, that'll come out to 100 times 100 plus 1 divided by 2, or 5,050. Okay. Similarly, you can do something very similar with the sum of k squared from 1 to n. And this is going to come out to n times n plus 1 times 2n plus 1 over 6. Okay, so for example, if your n is now 50, so summation from k equals 1 to 50 of k squared is going to come out to 50 times 51 times 101 over 6. All of that comes out to 42,925. Okay, so these would be difficult to evaluate otherwise, right? Otherwise, we'd have to sit there and add up 100 terms or 50 terms to determine this, but not when you have a closed formula. You can do the same thing for cubes. So we have the sum from k equals 1 to n of k cubed, and this closed formula comes out to n squared times n plus 1 squared over 4, which actually, interestingly enough, is the square of our first formula for the sum of k. Okay. So let's see how this works out. Well, if we make n is equal to 4, then we're going to have 4 squared times 4 plus 1 squared divided by 4, and that's going to come out to 100. So the sum of our first 4 cubes, 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed, will come out to 100. All right. And then lastly, we've got what is alternatively known as the geometric series or geometric summation. This is a sum from k equals 0 to n of a times r to the k power. R here cannot be 0. And then this summation is going to come out to a times r to the n plus 1 power minus a divided by r minus 1. And this may be written in a different format if you know it from calculus. Here, a is not going to be equal to 1, and r actually cannot be equal to 1 either. Otherwise, we'll have an undefined denominator here, right? But all right, so let's see a quick example. We've got the sum from k equals 0 to 5 of 3 times 2. So 2 is r, a is 3 here, raised to the k power. And then this is going to be, right, we just plug in the values as we have them, and that sum will come out to 190. All right, so this was a quick look at some summation formulas and how they can also have closed forms just like our sequences. All right, this was a quick look at all of these sequences, recurrence relations, and summations. I hope you found this lecture helpful. Please give it a like and subscribe so you don't miss the next one. Thank you for watching.